All right, let's dive in and crack the code of complex numbers. Now, I know it's one of those topics that can look super intimidating at first glance, right? But trust me, by the end of this, you're going to see they're not nearly as complex as they sound.
Yeah, I get it. You see a page like this, full of Z's and I's and those little bars on top, and your brain just kind of goes, nope. It looks like a completely different language. But here's the thing. What if it's a language with just a few super simple rules? Rules that, once you know them, unlock the whole thing.
Well, that's exactly what we're about to do. We're going to take this page right here and turn it from, well, that, into something that's totally clear. We're cracking this code together.
Okay, first things first. Before we can solve anything, we've got to know our main building block. I mean, every single problem you see here, it all comes back to the basic DNA of a complex number.
And this is it. This is the whole shebang right here. Any complex number, we'll just call it Z, is just a team of two parts. You've got the real part X and the imaginary part Y. And that little guy I, that's the star of the show. It's just the square root of -1. That's its whole job.
So, how do these two parts actually play together? Question 1 is a perfect little warm-up for us. It's asking us to prove something that sounds kind of wordy, that if you multiply Z by I, the new real part is just the negative of the old imaginary part. I know, sounds like a mouthful, but watch how simple this is.
Okay, let's do it step by step. We start with our good old Z equals X plus IY. Now, let's multiply the whole thing by I. We get I times X plus I times IY, which is I squared Y. Now, here's the magic trick. Remember what I is? The square root of -1. So what's I squared? It's just -1. So we swap that in, and suddenly we have -y plus ix. And look at that. The real part, the part without an I, is -y. And y was the original imaginary part. Boom, we just proved it.
All right, tool number 2 for our toolkit. And honestly, this one is the secret weapon, for real. It's called the conjugate, and it's going to make a lot of things way easier.
And you're going to love how simple this is. To get the conjugate, you just flip the sign of the imaginary part. That's it. Seriously. Plus becomes minus, minus becomes plus. Done.
Okay, so why is this simple little sign flip such a secret weapon? Well, check out question 3. It makes this pretty bold claim. It says, a complex number is actually a real number if and only if it's exactly the same as its own conjugate. Let's dig into why that's true.
Think about it this way. Let's go one direction first. If a number is real, like the number 5, what's its imaginary part? It's 0, right? It's 5 plus 0i. So what happens when you flip the sign on 0? Nothing. So of course z equals its conjugate. Now let's go the other way. What if we know z equals its conjugate? That means x plus iy has to equal x minus iy. How's that possible? The only way for that to be true is if the iy part is just 0, which means y has to be 0. And if the imaginary part is 0, the number's got to be real. It's a perfect two-way street.
Okay, so we've got the basic parts. We've got our secret weapon, the conjugate. Now let's talk about the size of these numbers. You know, their magnitude. In the math world, they call this the modulus.
Don't let the fancy name fool you. The modulus is just how far is this number from 0. That's all. If you imagine the real part x on one axis and the imaginary y on the other, it's just a distance. And how do we find distance on a graph? Good old Pythagorean theorem. It's just the square root of x squared plus y squared. That's it. It boils this two-part number down to one single value representing its size.
So let's put this to work. Problem 4 is a great example. It tells us, hey, we've got two complex numbers, z1 and z2, and the modulus of them multiplied together is 16. Our mission is to find the modulus of just z2. Now, you could multiply them out and then find the modulus, or you could use this awesome property that's basically a cheat code. It says the modulus of z1 times z2 is just the modulus of z1 times the modulus of z2. You can split them up. This makes problems like this one so much easier.
So, check this out. First step, let's find the modulus of z1. Using our formula, it's the square root of 2 squared plus -3 squared. That's 4 plus 9, so the square root of 13. Easy. Now we just plug that into our cheat code property. The square root of 13 times the modulus of z2 we're looking for equals 16. A tiny bit of algebra later, and we've got it. The modulus of z2 is just 16 divided by the square root of 13.
All right, we're ready. We've got all our tools on the table, we understand the parts, we've got the conjugate secret weapon, and we know how to find the modulus. It's time to put it all together and tackle the final puzzles.
And this is the big one. This is where everyone gets stuck. Division. I mean, what do you even do when you have a fraction with an I in the denominator? It just looks wrong, right? Okay, let's take question 9, part 3, head on. We have to figure out 7 plus 2i divided by 3 minus I. We need to get this into that clean x plus iy format.
And guess who's coming to the rescue? Our secret weapon, the conjugate. The entire trick to solving division with complex numbers is to use the conjugate of the bottom number. This is why it's so powerful.
Here's the move. We're going to multiply the whole fraction by a very clever version of the number 1. We take the conjugate of the denominator, which is 3 plus I, and put it over itself. See? 3 plus I over 3 plus I is just 1. So we're not changing the value of our answer, but we're about to totally change how it looks.
Let's handle the top part first, the numerator. We just multiply it out, FOIL it, just like regular algebra. The only thing to remember is that anytime you see an I squared, you swap it for a negative 1. Do all that, and it cleans up nicely to 19 plus 13i.
Okay, now for the bottom part, the denominator. And this is where the magic really happens. When you multiply a number by its conjugate, the I terms always cancel each other out. It's designed to do that. You're always left with a plain old real number. In our case, we get 9 minus a negative 1, which is just 10. A nice, simple, real number.
And just like that, the code is cracked. We've got 19 plus 13i all sitting over 10. Now we can finally see it. The real part is 19 over 10, or 1.9. The imaginary part is 13 over 10, or 1.3. That thing that looked totally impossible a minute ago, solved. So you see, what looked like a page of random, confusing symbols is actually a super predictable system with just a few powerful tools. And this isn't just about passing a math test. These exact rules, this is the language engineers use to design the electrical grid that powers your house. It's the language physicists use to describe the bizarre world of quantum mechanics. It's pretty amazing how this imaginary number has such a massive real-world impact. Kind of makes you wonder, right? What other hidden math is secretly running our world?